Okay, so did you all go through the Unit 2 book in radiochemistry? Did you all go through the book? And also, did you all go through the presentation? Now, this is the thing. So, if you don't talk, we can't get 100% out of these day schools. So, you need to get ready and you need to speak. Did you read the book? No? Not yet? Hmm? Right. So, before, before we start, I want to remind you on the CAT 2 exam. CAT 1 exam, we are still in the process of grading them. I could not upload the marking scheme yet, but I will do it very soon, okay? Perhaps tomorrow, all right? So I will upload the CAT 1 marking scheme on the on OULMS, and we are not sure yet, but we are right now we are planning to send you the answer sheets. Okay, so we will do it soon also once the grading is done. So CAT 2 exam will be on September 29th at 2:30 at university, exam hall 1. It is again a 1-hour on-site closed book test. It contains 25 MCQs. Usually 13 from unit 4, which is symmetry, and then 12 from unit 2. Okay, 25 MCQs. Right. So these are like online book chapters or videos. They are relevant to our radiochemistry unit, okay, unit 2. So if you need further reading or if the book is not clear in certain areas, you can always go to these online links or YouTube videos to understand it better. And even so, if you have any doubts, you can email me. So during CAT 1, I observed that many students ask many questions. So that's good. That's a good trend. But don't wait till the last moment. When day before CAT 1 or in the morning of CAT exam is not a good time to ask questions from me, because I am not readily available in that tight situation, okay? So start studying beforehand, start asking questions beforehand. Another thing is, don't ask questions just to get a pass in your exam, okay? That's not the purpose. Just to learn the concepts, to learn about this unit, you have to work hard, and I'm here to help you if you have any questions. So just to get a pass or just to get by the exams, that's not a good way to study, okay? So study for the content, for the material, to understand, all right? Study for the science. Okay. Right. So in this unit, radiochemistry, we talk about radioactivity. That is defined as the spontaneous emission, meaning without any external influence or stimulation, right? The nuclei or certain nuclides or the nucleus of an atom, they spontaneously emit particles or radiation. This is because why radioactivity happens. If you read the book or if you go through this if you went through this presentation, you already know why this happens. This spontaneous emission by a nuclei. Why does this happen? Why radioactivity occur? Certain nuclei do radioactivity, some don't. What's the key point? Why some are spontaneously emitting particles or radiation? Some nuclei. Huh? What is the reason? Why some are...
Electrons in the outermost shell is excites and
that's the... Now that's a basic error here. So these radioactivity, this nuclear chemistry, we are focusing on the nucleus, not the outermost shell electrons. So when reactions or changes occur in those outermost shell electrons, that's a chemical reaction. Here we talk about nuclear reactions. So those reactions,
releasing
those
of
change...
protons or neutrons, ma'am.
I'm sorry, not clear. Try again.
Releasing of protons or neutrons.
Yeah, so they are releasing from the nucleus particles. Some particles are or radiation is released, emitted from nuclei. I'm asking why it happens. Some nuclei undergo this radioactivity. Some don't. Why? What's the difference? What is the difference?
Some nuclei contain large amount of energy that they can't bear it, and
Sort of correct, but you all are not giving me those words I am looking for. So they are unstable, right? Those nuclei are unstable. That's why they spontaneously emit particles or radiation and fall into a stable position, or they convert into a stable nuclei. If your nuclide or nucleus is stable, that means unless that external stimulation is going to disturb you, unless such time that nucleus is stable and it is not going to spontaneously change or undergo nuclear reaction. Okay? All right. So that is radioactive. This is radioactivity definition. Now you know why it happens. Why it happens for certain nuclei and some not for some other stable nuclei. Okay, so it's already in the book and also in the presentation. Right. Now, look at this radioactive decay or radioactive reaction. So you have a parent nuclide. After the radioactive decay or that radioactivity occur, a daughter nuclide is created. So now it is being changed. So because some particles, subatomic particles are, or some particles, nuclear level particles are now released. See, some particles are released, or radiation, meaning energy, or both. They are released. Now, a somewhat stable or temporarily stable or nuclide is created. Let's say that this daughter nuclide is still not stable. That means that is also radioactive. Then it is going to undergo another reaction until this goes on, this spontaneous emissions happens until you end up with the stable nuclei. Okay. So here is an example where a nucleus, here it's specifically uranium-238, is emitting an alpha particle. Okay, alpha particle is actually now here you can consider, like, we are going to see these pictures in the next few slides. These white color ones are I don't remember whether it's neutron or proton. Let me go back and see. White color ones are the neutrons. Green color ones are the protons. So now here you can see the alpha particle contains 2 protons. So their atomic number is 2. And altogether we have 2 neutrons, 2 protons. So the mass number would be 4. So this alpha particle is released. Now it has a daughter nucleus, thorium-234. Okay. If it is stable, then the reaction stops here. If it is not stable, it is going to go or several radioactive activities or like spontaneous emission occurs until it reaches a stable nuclei. Okay. All right. So moving on, Here are some common particles that you're going to encounter when you talk about radioactive active decay or radioactivity. Alpha particle, I already introduced you. Then we have beta particles. Beta particles means basically a high energy electron. Okay. See, the mass number is 0 and the atomic number is -1. Why? It's an electron. Okay. Then positrons, actually positrons are the antimatter of beta particles or electrons. It has the same mass and other properties. It changes only in the charge. It's a positively charged particle. Okay. It's like an electron with by the mass and all, but its charge is positive, positron. Then proton. Proton we indicate as P. So atomic mass, atomic number is 1 and the mass number is also 1. Then neutron. Neutron is neutral. Okay, so no charge. Therefore, the atom, the number of protons or the what we call atomic number is 0 and the mass number is 1. Okay, and then gamma rays. This is the basic radiation that we see during radioactive decay. All right. Okay. Here are some different types of radioactive decay modes. So decay types. You can see alpha decay. That was our first example. See, a beta particle is emitted. Okay. And whatever is produced is now, since it's a beta particle that reduced, so the production or the daughter nuclide is 2 amounts shy when it comes to atomic number, 4 amounts shy by the mass number. Okay. So that depends on, like, it's because of the energy conservation rule. Okay, energy and matter conservation rule. So the matter that is being removed as a separate particle is now go from the nuclei. Okay, very simple. Then on the beta decay, we there are 2 ways. Negative beta decay means that an electron is released. In the positron emission, or the positive beta decay is a positron emission. So positive positron is removed. So accordingly, your resultant product has different atomic number based on that emission. Okay, mass number is not going to change. Why? Because the emitted positron or the negative electron has no mass. So the mass is going to be the same. All right. If not, anything is not clear, immediately ask me. Okay. Then we have another type of radioactivity, electron capture.
Excuse me,
here,
madam, your voice is not clear.
I'm sorry?
Your voice is like not clear. At certain point, it's like getting stuck.
Oh, sorry. Is it okay now?
Yeah, madam.
Okay. All right.
Yeah.
So, okay, we'll see. If it is not clear, let me know. So in the electron capture, now electron is captured. Now see, the electron is now in the left side of the equation. Now here, the nucleus, around the nucleus, we have the electron, the energy levels or orbitals or the electrons hanging around, okay, orbiting around the nucleus. So those electrons that one can be captured by the nucleus, okay, we call, when that electron that is captured by the nucleus, if it is from the K shell, we call it K capture. Now the electron is captured, okay, by the nucleus. Now what happens in your outer shell, like in that electron or the energy levels where the electrons were residing, now one electron is missing. So we have a vacancy there. Then what happens? So now let me draw a basic idea. So this is your nucleus, and then around that you have, this is just an exaggeration, okay, it's exaggeration. So you have your electrons floating around, isn't it? So one electron is going to get absorbed to the nucleus, electron capture. When that electron is gone, now we are creating a hole. Now what happens? From upper levels, okay, one of the electron is going to jump into that vacancy, releasing that excess energy it had, because it's going down to a now lower energy level. So some extra energy is with it. So it is going to emit that energy. So that energy, because of that, usually when an electron capture happens, you can observe that X-ray is emitted. When the electron capture decay happens, or the electron capture reaction happens, usually it followed by an X-ray radiation coming out of the atom. So that is because this hole created by the electron capture is now filled by the high energy electron. Okay, right. So I'm going to erase these. If you look at the video, you can see these. Therefore, I'm going to erase. And then gamma decay is simply emission of energy, radiation. So the mass number or the atomic number is not going to change. It's just an emission of energy. So the excited nuclear state is going to now come to a non-excited or the ground state nuclear state. Right. So as I said before, if you carefully go through, these nuclear reaction equations are easy to build. Okay, you just have to consider two things. The mass numbers of the both sides has to be equal. Mass should be conserved. And then the charges should also be equal from the two sides. Okay, that means you have to balance the mass numbers and also the atomic numbers. All right, so that is the only thing. Now just imagine here, so uranium-235 is going to undergo alpha decay. So now initially it had atomic number 92. When the alpha particle is removed, the resultant daughter nuclei has atomic number 90. All right. And if you look at the mass number also, 235. Now here 4 plus 231. Look at the second one here. If a electron is emitted, that means beta negative emission. See, 6 atomic number for carbon. Once the beta emission happens and the nitrogen created, it becomes 7. Why? Because -1 is emitted. 7 plus -1 is equal to 6. All right. Likewise, you have to consider these conservation laws to balance the masses and also the charges in a nuclear equation. Right. Did you all try these equations at home? Now, when you are doing these kind of questions, either they have to tell you, like, sometimes it's difficult to keep in memory all the elements and the atomic numbers in the periodic table. So if it is needed, we will provide you a periodic table, or we will give information. Like here, look at B. Thorium-231 decays to form protactinium-231. See, we give the product. So you don't have to worry about what is being produced. But if it is not given like that, then you have to refer to a periodic table. Okay. Anyway, now quickly take your 1 or 2 minutes and try these equations. Like, did you try the first one? Thorium-232 undergoes alpha decay. What is being formed? Did you try? Did you try?
It undergoes radiation. Atomic number will be 28, and the alpha ready.
Yeah, so what you are going to do is you are going to try to write the equation. So you have thorium. They say that alpha decay happened. So you are going to write alpha, and then you are going to try to balance the mass number and the atomic number. Now it is 92 is out. So it has to be 88 atomic number. And then 232 was the initial mass number. Now 4 is gone. So it should be 228, isn't it? So what is the element which has the atomic number 88? That you have to look into a periodic table. Now tell me, what is the element here? What is the element here? Atomic number 88. Don't be lazy. Look at your periodic table and let me know.
Radium.
Hmm? What is the symbol? What is the symbol, Putta? R.
A.
Is RA. Is it correct? RA the. I'm asking you because I don't know. I don't remember. What
If
is
it is radium, it is Ra.
radon? Radon, okay, not radium.
Radon RH.
Hello? 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 Guys, can you hear me?
Yes, madam.
Hello? You all
Yes,
can
ma'am.
hear me, right? Yeah. What did you say, Putta? I couldn't hear. Hello? Is it radium or radon? Hello? Can you all hear me? Is it my connection? What is it? Hello? Wait. Hello, can you all hear me?
Ma'am, it is radium and Ra symbol is.
Yes, yes. Okay. I couldn't hear. Yes, okay. So, that first one is okay. Yes, radium. Then what about the B? That is again, now this one is easy because thorium-231, it's already given, and then the decay and the product is also given. 231 protactinium. Okay. So what we are going to do is again very easy. What is missing here?
Beta minus.
Is it a beta minus decay? We'll see. So we don't know what is going to be here then, but we have a protactinium 231 91. So yes, it looks like, isn't it? Because see, the mass number is not changed. So it is the same. So we don't have any problem there. But the thorium 90 now converted to 91 protactinium. So that means we have to have -1 here. Sorry? Is this okay?
Should be beta minus, right?
Yeah, okay, good. Right, so let's go for C. Potassium 40 undergoes positron emission. Okay, so we have potassium 40. Okay, they don't, what is the atomic number of potassium?
90.
Okay, then it undergoes positron emission, meaning so no mass number, but there is a +1 atomic number. Then we have to figure out what is the compound. So +1 indicates that we have to have the atomic number. What should be the atomic number? What should be the atomic number here? 18. Right. What should be the mass number?
40.
So what is the compound we are looking for? The element that is, sorry, that has an atomic number of 18. Yes, go ahead.
Neon.
Okay. Right. So you understand how to get these done, right? Okay. So answers anyway here are 18 argon. You all are making me.
Yes, this is argon.
Yeah. Right. So another question. Predict the products of the following processes. So we are not going to spend a lot of time here. Can you quickly figure it out, somebody, for question A? Very simple. So radon 86 is going to undergo alpha decay. Quickly, someone tell me the answer. You just work on your paper and let me know what is the product. Now we did 3 examples here. So quickly.
Polonium 84.
84. Okay.
Polonium.
Polonium, PO.
Yes, 220, 216 mass number.
Okay, now I want someone else to answer for the B. Thorium 234 undergoes beta minus. That means electron decay. Someone else tell me the answer this time. Give me the answer, please. Someone give me the answer.
It's protactinium.
Give me the atomic numbers and mass number, please.
The big number should be 91. Should be 234.
234. Is it protactinium? I'm not. PA?
R.
I'm not sure because I have to look for the periodic table and see what is 91. What is 91? We have the answers in here. I can, go and check. 91. Let me see. I'm looking. Oh, yeah, protactinium. Okay, good. All right. Okay. Okay, moving on. So you guys have an idea how to balance these nuclear reaction equations. All right. You just need to balance. You don't need to know what is 91, what is 88. That's not the point here. That information I will give. If needed, I'll provide you the periodic table. The point that the logic you need to know is how to balance them in terms of the mass number and the atomic number. All right. Okay, so now let's go into radioactive decay kinetics. Now, you have to understand this simple thing. What is that? The, the radioactivity or the spontaneous emission is actually a random process. That means if you have just one atom on your hand and you are waiting, just hypothetically, okay? One atom in your hand, and you're waiting for it to decay. Let's say it's a radioactive element, isotope, so you're waiting for it to decay. You don't know when it will happen. It can happen immediately, in 5 minutes, in 10 minutes, or it could take several thousand years. Okay, even though it has a half-life is defined for a amount, a quantity, or bulk material. Okay, so for one atom, it's a random process. You don't know when it is going to decay. Do you understand what I'm saying? At the atomic level, it's random. It happens spontaneously by itself. You don't know when it is going to happen. But there's a probability of happening. Okay, if there is a lot of such atoms, so it's just not one atom. I just took the hypothetical case. When you take, let's say, 1 milligram or 1 gram or 1 kilogram, then it's a lot of atoms, right? So all of these atoms have their individual probability of happening. Now with that, with a bulk amount, now at a certain given point, at least one will be spontaneously emitting or radioactively decaying. Okay, do you understand what I'm saying? So based on that, this quantity-wise, this is radioactive decay law is built up. So that's the probability per unit time that a nucleus will decay is a constant. Probability per unit time that a nucleus will decay is a constant. It is independent of time. See, it's a random process. That's why it is independent of time. And this constant is called the decay constant, or we call it lambda. Okay. So here the rate of decay, okay, rate of decay, or in other words, that we can say how many will decay per unit time, right? So rate of decay of a radio element at any instant is proportional to the number of its atoms present at that instant. It depends on the number present. Okay. All right. So that's why, based on that basic idea, we can write this minus is there because we are talking about a decay. So the number of atoms present is going, the dN divided by dt, that is the decaying rate, is directly proportional to the number of atoms present. All right. That constant is lambda, or the decay constant. Okay. All right. Now what happens here? I'm just rearranging it. This is for a minute time. Okay. And I have rearranged it. And then I'm going to integrate both sides. All right. So it's not given here. So what I'm going to do is, wait, I'm going to write it. Okay. And then that is going to say 1 over n integrated by dn. So you are going to get ln n. And if you consider the time limit 0 to t, you are going to get ln nt minus ln n naught equals minus lambda t. Okay, then it's a simple rearrangement and you are getting this equation, which you should remember. Okay, once you know this equation, all right, you can do a lot of calculations based on radioactivity decay. All right, because at a given time, if you know the quantity, the starting quantity, after a given time, you can see how many is remaining in that radioactive sample if you know the lambda value, which is the decay constant. All right. If anything is not clear, let me know. All right. Okay. And then that is lambda. We define lambda, decay constant. All right. Then we are going to define another term, activity. Activity of a radioactive sample is the rate of decay. Okay. Rate of decay. That is number of decays per unit time. So disintegration, decay, it's the same thing. All right. Decay or disintegration. Now, that is we already know, right? Because rate of decay we already discussed. See, this is our rate of decay, isn't it? Okay. So that means A is actually equal to lambda n, right? Lambda is the decay constant. I hope you remember. Now, since n equals n naught e to the power minus lambda t, all right, that happens because the len is removed. I hope that is the math part, okay? I'm not going to explain that. I hope it's clear for you because now we are in level 4. Still, if you don't know what is happening here mathematically, not theoretically, mathematically, I advise you to go back to your CYE 3200 books or to your maths friend to learn about those, okay? Anyway, so since A equals to lambda n, we can easily replace n equals n naught this equation by A equals A naught e to the power minus lambda t. So what is A naught? A naught is the activity you observe at the beginning of a sample for during a given time period. Okay, you will understand this better when you apply these in questions. Okay, anyway. So this activity or the rate of decay for a sample, you can calculate by a radiation detector, okay, Geiger counter or something. And in that case, the count rate is equal to the counting efficiency of that particular detector and the activity. I'm just showing this equation here because it's in your book, but it's just very simple and you sort of understand what it means, all right? It makes sense, right? Count rate is linearly proportionate to the activity. Of course, that makes sense because activity is the rate of decay. All right. And here I also put specific activity in my slide because at some point, I think in session 4, the book talks about specific activity. All right. So here specific activity is the rate of decay per unit mass of the decaying material. All right. So we'll see when it is there. Okay. All right. Then I'm going to introduce you to another term, half-life. You already know what half-life is. So what do you know about half-life? What is half-life? In general sense, because from level 3, for kinetics also you learned about half-life.
The time taken to reduce the concentration of the material by half of its initial value.
Very good. That's half-life in general sense. So it's same here. That is the time needed for a given amount of the radio element to decay exactly to its half of its value, the amount. Okay. See, it's given nicely here. So initially you had 10 grams of carbon 60. It's radioactive. And after one half-life amount, that is 5.27 years for cobalt 60. Okay, for cobalt 60, it is 5.27 years. Okay, so after 5.27 years, it is the activity, radioactivity is going to get down to 5 grams. It doesn't mean that the cobalt 60 is going to get reduced to 5 grams. That's not what it means. If the radioactive quantity is like it's at 10 grams, now the active other 5 gram is now already decayed. That's what it means. Do you understand that part? So cobalt 60 is the radioactive sample, okay? And then after 5.27 years gone, cobalt 60, which is the radioactive component, is only in 5 grams. What happens to the other 5 grams? Did it vanish? Huh? What happened to the other 5 grams? Tell me that. Because this might be somewhat, this values might be somewhat misleading to you. So tell me what happens to the other cobalt 60 amount, cobalt material. Huh? Tell me what happened. Is it gone? Is it vanished? Tell me. Now just think about it. Now what happens during a radioactive decay, what happens? Now let's go back to an example here. Now you should be able to tell me. Here, let's say, now you had thorium-232, here thorium-231. After decay, it converted to protactinium-231. Now, let's say after one half-life, the amount of thorium-231 is now reduced by half. But now it is in the form of that reduced amount. So the missing thorium is now in a different elemental form, protactinium. Do you understand what I'm saying? So in this case also, after 5.27 years, cobalt-60 is no more there in 10 grams, but it is in a different elemental state. So that for that to know what is that, we need to know the decay reaction. Do you understand what I'm saying? So if you just look into literature or look into a book, you will see that it is going to convert into nickel. So what happens is only 5 grams of cobalt-60 is going to remain. The rest of the 5 grams will be in partially in the nickel form, and some are now gone. It could be, I don't know what's the emission. It could be gamma or alpha or beta or whatever that other missing particle. Do you understand what I'm saying here, guys? Is it clear? Is it not clear or is it clear?
Clear, madam.
Okay, right. So likewise, in every half-lifetime, the amount of the radioactive sample is going to reduce by half. Okay, so that is half-life. Very good. Now, if you use this equation at the half-life time, okay. Oh, my pen is not working. Okay. So if you apply this equation for the half-life time, for this general equation, you will see that at the half-life time, the NT is going to be what? Half of the initial amount. So N naught divided by 2, half of N naught, okay, at T half time. All right. So we can apply that here for the equation. If I apply that, lambda T half equals N naught. Wait. They have rearranged it, isn't it? Wait, my pen is not writing properly. So this is just simply converting len into log. Okay, log, and then here we have n naught. At the bottom, in place of nt, we have now the half of n naught. Why? Because this is t half time. Now, once you solve this, you will see t half equals 0.693 divided by lambda. What does this mean? So, once you know the half-life for a particular radioactive sample, you can directly get their lambda value because it is 0.693 divided by t half if you want lambda. Okay. So this is a very important relationship that you will need in your calculations. Now let's see an example. So now this carbon 11, the half-life is given as 20.4 minutes. Okay. What percentage of the original 1 milligram sample of carbon 11 is left after a 1 hour 42 minute period? Okay. So what percentage of the original 1 milligram of sample of carbon 11 is left after a 1 hour and 42 minutes period? So this is some calculation. All the information you need is here. See, you have your general equation and also the T half and lambda relationship is also known. So how do you apply it here? So 1 hour 42 minutes. Now you have to be very careful when you are doing this kind of calculation. You need to know, you need to make sure that your time is in the same unit. Okay, that is important. All right. So if the half-life is in 20.4 minutes, your the time that they are talking about should also be in the minutes form. Otherwise, you will be your answer will be wrong. So think of a way to handle this or tackle this. So this is very easy. Can I give you 2 minutes to solve this question? What is the answer you have? Anybody who already did this question? What is the answer you got? Anyone? So 1 hour 42 minutes is actually 102 minutes. But anybody got an answer for this question? No? So how do you tackle this question? What percentage of the original 1 milligram sample of carbon 11 is left? So it doesn't matter because we don't have to go for milligram calculations because they ask for the percentage. What percentage of the original sample of carbon 11 is left? So our equation is T divided by N0 equals e to the power minus lambda t. Okay. So what is this? The existing at the moment, like, you know, N naught is the initial quantity or amount or the number of atoms of the carbon 11 sample. And then NT would be the number of atoms remaining, carbon 11 number of atoms remaining after the considered time period, which is 102 minutes, right? So this is actually the percentage. The remaining, what percentage of the original 1 milligram of sample of carbon 11 is left? This is what it is. If you just simply get the percentage of this value, that is the answer you are looking for. Now it's very easy. So you just have to solve the other side. E to the power minus. Now we need lambda. How do we know the lambda? They are not given the lambda, but they have given us the half-life. So we know that lambda equals 0.693 divided by t half. Don't we know it already? We know that already. So lambda is easy. It's just the 0.693 divided by the half-life. But we have to make sure now this is in the per second value. And the t, the time we are considering is 102. That is also in minutes. This is also in minutes, no issue. That is the ratio, NT divided by N naught. But we are looking for the percentage. So we are going to multiply it by 100%. The answer to this equation, this part will be the percentage remaining of the sample. Okay. So the answer will be 3.125%. Now look how they have used a logical explanation to get it without doing the equation. So what I usually like is I prefer to apply the equation because it's like, you know, it's easier. Okay, less time consuming. But this question is easy. It can even solve by thinking in a logical manner like this. See, 102 minutes. You can read this. 102 minutes means 5 half-lives because one half-life is 20.4. All right. So when you think about it, after every 20.4 minute, it is going to reduce the amount by half. So after the first half-life, you are going to get only 50% of the carbon-11 remaining. Then in another half-life, 25%. In another one, 12.5. In another one, 6.25. In another one, that is the last one, 3.125. So likewise, logically also, you can obtain the same answer. Right? Because this the question is easy. Anyway, any questions here? Okay, no. Then we are moving on. Calculate the activity of 1 milligram of pure radium. Okay. And the T half is given 1600 years. But in becquerel, that kind of question you can get. Becquerel. So if they ask you to keep the activity in a certain unit like becquerel, now usually usually we keep the activity, the rate, that is the activity is defined as the rate of decay. Okay, so in other words, you can just say number of decay per unit time. So you can say per second how many. Likewise, you can keep. But if they want us to keep it in becquerel, you need to know that indicates you have to keep it in the disintegrations or decays per second. You can't keep it in per minute, per year, or any other way. You have to keep it in per second. All right. So here you have to, no percentage or anything. You have to specifically calculate activity. Okay, specifically calculate activity. So in that case, you have to actually calculate. See, lambda into n. A equals lambda n to n. Lambda is easy. It is, of course, 0.693 divided by T half. Because T half is given. Now, since they are asking it for per second, you have to convert your T half into seconds. That's what they have done here. 1600 years multiplied by 365 multiplied by 24 multiplied by 60 multiplied by 60 again. Okay. So this is actually your lambda in per second. All right. And then number of atoms of radium. Okay. Number of atoms of radium. So for that, they are given us that it's 1 milligram of pure radium. Okay, 1 milligram of pure radium. So what you do is 1 milligram converted to gram, and then the moles of radium, number of moles, and then multiplied by the Avogadro number to get the number of atoms. Number of radium atoms. Okay, right. Clear? I hope it's clear. Okay, now you understand what radioactivity, and it keeps going. As I said at the beginning, it keeps going. The radioactive nuclei keep decaying until it reaches a stable nuclei. Okay, all right. So let's say here at the beginning, as I said, let's say that your daughter nuclei created is not stable, then it is also radioactive. It is going to go into another decay process or spontaneous emission. Another nuclei created. If that is not stable, it is going to go further. Likewise, it is going to go in a chain until a stable nuclei is reached. Now in nature also, there are such radioactive decay chains, or we call it radioactive decay series. And those radioactive samples exist on Earth is going to continuously, this is spontaneous emission, okay? By on their own, without any external stimuli, they are going to keep decaying, all right? There are 4 major such decay chains observed in nature. One is thorium, okay, that is thorium-232 decaying process, then radium or uranium series, then actinium series, then neptunium series. So there are symbols that is indicating these decay series. Here thorium we call A equals 4n. For the radium we say A equals 4n plus 2. So what are these values? What are these symbols that we use here? So that those are actually the mass numbers, and if a mass number of that the starting what you call parent nuclei, if it is divisible, perfectly divisible by 4, we call it A equals 4n series or 4n series in simple. See, it's 232. That is perfectly, you can divide the 232 perfectly by 4, right? But if you do the same for radium or uranium series, the 238, you can't perfectly divide it by 4. 2 is going to remain. Okay, that's why we call it 4n plus 2. All right. Likewise, you understand what these values are about. Okay. Anyway, so there are 4 natural decay chains. All right. Because you might think why it is not done yet. Because it's not done yet, you will see some of these early parent nuclei have very, very long decay half-lives. Okay. They are very long. So that's why it is like going forever for those decay series to go on. It's still going on. Now, Neptunium is not that significant because now, because of the short half-lives of the species involved in Neptunium series, it's now going to, like, the chain, the reaction chain is not about to go out. Okay, but other 3 substantially they exist. You will see in the next slide, I have an example. I don't remember, maybe it was a thorium. We'll see. Now, anyway, all these series, they are keep producing radioactive daughter nuclei because of they goes on, okay? Right? Once they are reaching the end of these decay series are a stable nuclide, of course. For the first 3, okay, for the first 3, in all first 3 decay chains, the stable end product is actually a lead product, okay? Now let's look at an example. It's a thorium series I got as an example. See, it start with which one is better looking? Okay, we'll go here. So you have thorium, and they go what do you call the decay? First, they decay into radium, and it takes, see, millions of years. All right, several hundred years for that decay to happen. Okay, and then that radium is going to take, the half-life is 5.7 years and convert it to actinium. See, it is going under beta electron emission or beta negative decay. Then that again another thorium isotope, 228 thorium, right? And then it goes on, another radium, and then xenon, and then polonium. Likewise, it goes until it comes to lead 208, which is the stable isotope, okay? Which is the stable isotope. So it goes on. Now just imagine, let's say just 1 thorium is converting to radium. Oh, not converting, let's say use the proper word, decayed to radium, and then that atom is going to go, like, at some point, right, it's random emission because it's atomic level, if I just consider 1 atom, and it is going to decaying to actinium. Meanwhile, another thorium is now after so many several years, it is going to decay. So because these have very long, what do you call, the longer half-lives, all these species exist at the same time. Do you understand what I'm saying? Once, like, several thorium is created, still that original thorium sample is going to be there because its half-life is very, very long. Several thousand years, okay, billion years. Do you understand what I'm saying? Million years, sorry, going to say, okay? So all these species going to exist in nature because the early parent nucleides, early daughters have longer half-lives. All right. So this is only just thorium, just to explain. Likewise, we have radium and actinium and neptunium series. You can Google or look into books to see what are the products and all. Okay. All right. Here is a question actually I got from one of the past papers, recent past papers. Here is part of a decay series. Okay. So part of a decay series is given, and in some cases they are asking what kind of decay type happens. And in some cases they ask what are the products of these decay steps. Will you be able to do this kind of question? Can you do this? Do you want me to show it? Do you want me to explain it? This is easy, right? Because it's just simple alpha and beta decays. So we already learned one or two few examples. So I don't think that I need to explain. Do you want me to explain? Shall we move on? So silence indicates that you don't want to. So answers are there. You just do it by yourself at home and see whether you got it correctly. Right. Now, as I said, so like, after a while, so when one parent nucleide keep decaying and depending on its half-life, the daughter nucleide is coming up. And if that is also radioactive, that also going to take some time to decay. So likewise, this is going to happen. So eventually they are going to, if let's say both the parent and the daughter nuclei, we are just talking about just one step here, if those two are both are radioactive, they are eventually going to go into a radioactive equilibrium. Okay, so that equilibrium can be called secular or transient depending on the differences of their T-half values. Okay. Now, as an example, we say they reach to a secular equilibrium if the T-half of the parent is very, very large compared to the daughter nuclei. As an example here, between thorium and radium. See, the thorium here, it's like several million 10 to the power 10 years. Okay, so it's millions of years, right? But compared to that, radium has just 5.7 years. So these two are going to encounter with a secular equilibrium. See, you can understand it here. See, this is the activity of a parent nuclei. It is giving an activity, and since the half-life value is very, the activity is going to be constant because the huge amount of parent nuclei is there. So this is showing longer because the T half value is huge. And then once few of the parent nuclei is going to is decayed, now the daughter nuclide is created. Once the daughter nuclide is created, if that is also radioactive, it is also going to now show the activity, right? So the daughter nuclide is keep creating because the parent nuclide is decaying. And the daughter nuclide is also going to show activity. But because its half-life value is smaller, their activity is going to go in this curve nature. Why? It is keep producing, and it is showing the activity. Why? Faster than the parent nuclei, the daughter is undergo the decay. So it is showing activity. Okay. And then eventually they are going to come into the same activity value. That means the parent is slowly producing the daughter nuclei, then the daughter nuclide is going to quickly decay because comparatively, this is a relative thing. Relative to the parent nuclei, the daughter nuclide has a smaller half-life. So they come to an equilibrium, which we call secular equilibrium, and the T half values are going to be that happens because the T half here, T1, T2 indicates the T half value of the parent. Shall we write it as parent and the daughter? Okay. So this kind of secular equilibrium, if that is reached for a step, we can write it as this. You don't need to know how to derive this. It's just, we can say lambda 1 n1 equals lambda 2 n2 after the equilibrium is reached. Okay. A decay constant for a parent nuclide, and it's the amount of amount of the atoms present equals to lambda, or the decay constant of the daughter, and the amount of daughter atoms present. Okay. Now let's say the parent half-life is not that, it's bigger, but it's not very huge compared to the daughter half-life. As an example, here we can say this one. See, here the radon is 55 seconds, polonium is 0.14 seconds. That is also too big, no? What can we get as an example? So that's also, it's fine. We can consider them as 55 seconds and 0.14 seconds. So they are not as deviated, or there's no huge difference like in this step. Okay. In that case, when of course the parent nuclide has a bigger half-life, but they are not comparatively huge, largely bigger than the daughter nuclide half-life. In that case, you are not going to see this sort of like unchanged activity for the parent. The activity is going down now with time. Why? It's not hugely larger compared to the daughter nuclide half-life. Okay, it is going down, not a relatively constant value like this. Once the sum of the parent nuclide is going to decay and the daughter nuclides are created, now they are going to show the activity. It keeps increasing because the daughter nuclides are getting created, and after a while they reach the equilibrium. They're all going down. Why going down? Because we can see that they are together going down because they have comparably or relatively closer half-life values. Okay, parent value is bigger, but there's no huge difference between them. Okay, all right, so that you can visibly see that they are decaying. All right, so in such case, we call it's a transient equilibrium. At the transient equilibrium, once the equilibrium is reached, you can use this equation. Again, you don't need to know how to derive this, and I don't expect you to know these relationships as well. If it is needed for you to have it in your question paper, I'm going to give you these equations. All right. Then at the beginning, I told you this spontaneous emission occur because some nuclides are stable and some are not. Okay, the stability matters. Only a few nuclides are stable and others are not stable. We call them radioactive nuclides, and they always try to undergo spontaneous change to become stable. All right. Then here are some nuclide types. We have isotopes. Isotopes means they have the same atomic number. They belong to the same element, but their masses are different. You already know. So this is an example. Then isobaric nuclides, their mass are the same. See, mass numbers are the same, but they belong to different element groups. Okay, they can belong to different element groups. Then isotonic. Isotonic means they are the neutron number are the same. Okay, neutron numbers are the same. So that you can't visibly see. You have to deduct and see how many neutrons are there here, how many neutrons are there here, how many neutrons are there here. You will see in all cases there are 10 neutrons. Oh, is it 10? Am I wrong? 20, right? 20 neutrons are there in each case. Then isomeric nuclei. So in the isomeric nuclides, so they do not differ in atomic mass, atomic number or the mass number, but they differ in their energy wise. So various energy states are there for the same nuclei. So if they are in, like, you have the ground state, okay, the lowest energy state, and they are in a very high energy state, but they are short-lived, meaning that they immediately come down to the ground state. Those kind of temporary states we call excited. Okay, so excited nuclides. And if that higher energy levels have like longer half-life values, or that, in other words, that means that they are going to trap in those excited states and they are going to stay for a while, we call those metastable isomers, or meta. M is going to be there to indicate that. See, so this is scandium 46M. That means it's a metastable excited state, not the ground state. Okay, so ground state here denoted with G. All right, so these are different categories based on the A and the Z values. All right, anyway, we will talk about this neutron to N to Z, neutrons to atomic or the proton number ratio. Because if you consider a nucleus up to atomic number 20, usually the stable nuclide have 1-to-1 ratio of neutrons and protons. But when you go higher than atomic number 20, now the nuclei are heavier, and naturally the protons, they are positively charged. You can't keep those same charge quantities together for a longer period of time. Why? Because they are repelling each other. So when you have larger and larger number of protons together, it's very difficult to keep them together without repelling each other. Okay, so they will collapse if there are so many more protons. So in order to relieve these proton-proton repulsions, you need a lot of neutrons in there. Okay, so that's why when the atomic number is higher than 20, there are so many neutrons than the protons. Therefore, the neutron to proton ratio is more than 1. All right, so that is to overcome these electrostatic repulsions between protons and protons. So look at this one. So this is very interesting chart. In this chart, in the y-axis you have neutron number, in the z-axis you have proton number. Now what happens is, up to 20, this I forgot to tell you, this blue line is the non-radioactive, meaning stable. These are the stable nuclei. You can see up to 20, this stable nuclide range is going to align with this black line. So this black line is where the N to Z ratio is 1. Okay, that means protons and neutrons are in the 1-to-1 ratio. Afterwards, the stable elements or nuclides are deviating from the 1-to-1 ratio line and it is going upward, meaning more and more neutrons are there. So in order for them to be stable, you need more and more neutrons. That makes sense because we know why. The reason we know, to overcome the electrostatic repulsion. So what are these green color belt? Those are the existing nuclides. Okay. So many is existing. So many are existing. But the stable, naturally stable ones are only denoted in blue. Okay. Those are the stable nuclei. There are many more nuclides available exist, but they are not stable. They are continuously decaying. All right. Okay. So, yeah. Here, after 83, that's also another good point. So, after 83, no more stable nuclides for any element. So they are all the existing afterwards, after 83, all the nuclides or isotopes available, they are unstable or radioactive. Okay, right. So if you take just let's say the element 40, okay, you take element 40, you can see there are so many isotopes. These are all isotopes. Why? Why I'm calling them isotopes? Because they belong to the same proton number, 40. All these, there are so many isotopes, but very few stable isotopes. Everybody else is unstable. I hope you understand how to read this chart. Now, if I explain it further, you will see that, so this black one is the stable isotopes. The isotopes above the stable line, okay, stability belt, they are very rich in neutrons. See, this is the neutron number. So higher means they have higher neutrons, very rich, very high. Of course, they have higher than protons, but very, very high compared to protons. In that case, they tend to, now they are going to decay, right? Because they are not stable. So they are going to decay via electron emission or beta minus emission. Okay. There, what happens? They have lots and lots of neutrons. They are going, some of these neutrons are going to convert to protons so that they can go down, collapse down and get closer to the stability belt. Okay. So these radioactive unstable nuclei want to get closer to the stable area, stability belt area. So if they are above the stability belt, that means they are very richer in neutrons. They are going to convert neutrons to protons by electron emission and get closer. If they are below the stability belt, that means still they have a lot of neutrons than protons because they are above the 1-to-1 ratio, but they don't have much neutrons as the blue area ones. So those cases, they are going to undergo beta decay or the electron capture, meaning the protons are converted to neutron, so that they can go upper in the line and get closer to the stable area, stability belt area. Let's say that above 83, they want to get down to the stability belt. What they do is they are going to go via alpha decay, hugely reducing their proton and neutrons and trying to get closer to the black stability belt. Okay, got it? Understood this point? Can you explain this chart? And can you explain, based on their position, can you explain whether they are going to go through a beta decay or a positron decay, electron capture or alpha decay? Can you explain that? But like, remember, these are not hard and fast rules, okay? You can predict based on its position in this chart what kind of decay process they may undergo, okay? Though that's not a confirmed or firmed rule, not a principle, just a rule. All right. So with that, can you predict the mode of decay for boron 8? Someone? Can you predict? Now quickly write down on a piece of paper, write down how many protons are there, how many neutrons are there, see which is richer, then you can predict. So what is the atomic number of boron? What is the atomic number of boron? Hello? So if you don't talk, I'm not going to continue. Look at your periodic table and let me know.
5.
Okay. So how many protons are there? How many neutrons are there? Quickly, please. We will not be able to discuss everything if we are going to take this much time.
Proton 5.
Yes.
Neutron 3. Sorry, neutron
Now,
3.
what do you... sorry. Sorry, I couldn't hear the last bit. I disturbed you. Tell me.
No, ma'am, correct.
Yeah, it's correct. Now, tell me what kind of decay mode can we expect for boron? So, it's richer in this case, it's richer in proton. So, what do we expect? Now, let's go back here. It's richer in protons, okay? Actually, they are somewhere here. Richer in protons, okay? Not over here. So, see, it's richer in protons. So, we expect it to go up. For it to go up, what should it do? Should convert protons into neutrons. So, what kind of decay mode are we expecting? Huh?
Ma'am, sorry for interrupting. That part I
Uh-huh.
didn't understand, ma'am.
Which part?
Because the decay mode, how to find it? Because
See,
just now we came from practical.
is it? You had practicals today?
Yeah, ecology practical.
Oh, okay. So I have recorded this lecture. I will update, I'm going to upload it. So you will not miss anything much, okay? So I explained it already. Since we don't have time, I'm not planning to, sorry about that. I'm not planning to
That's
explain this.
that's okay, ma'am. Sorry
Explain.
about that. I couldn't answer you.
It's okay. So someone else, there were several here. So tell me, what kind of decay mode are we expecting here? If it is proton rich. So someone tell me the answer. There are so many here, 27. What is the answer? No one knows. Anyone? See, in that case, if the protons are richer, you want to go up. See, you have to get rid of some protons and get more neutrons. That means you have to undergo be it a positron or electron capture. Okay, so that's what you do. See, in this case, either positron emission or electron capture. Likewise, for fluorine 22, if you calculate, you will see it is going to go through electron emission. In other words, beta minus emission, because it has higher amount of nitrogen neutrons. Okay, right. Then let's move on to nuclear binding energy. Like in here, now a nucleus is now made up of protons and neutrons. They have come together, staying closer and combine into a tiny nucleus when an atom is formed. So when that happens, what is observed is that some amount of mass is going to be missing because that is converted to nuclear binding energy. So that loss of energy is going to make the nucleus stable. All right. So in other words, if I tell you, if you take a nucleus, there are certain number of protons and certain number of neutrons are together. The total mass of that nucleus is going to lower than the individual masses of the same amount of protons and neutrons. Okay, so there is a difference. So here it says a nucleus has less mass than the total mass of its constituent subatomic particles, which are protons and neutrons. Okay, so that missing mass, what happened, we call it mass defect. During the formation of that nucleus, that mass, lost mass, is converted to energy and released as binding energy. Okay, so that stability of the nucleus is gained through that mass defect. Okay, now here is a nice graph showing the binding energy values per nucleon, and you can see, and this side it's a mass number, and see it is going up and there is a maximum. Okay, maximum period around the iron and cobalt and nickel area. Okay, iron, cobalt and nickel are the most stable because they are having the highest binding energy values, and then some values around 7.7 and 8.4 areas. Okay, all right. So when it comes to now later on, you will learn about some nuclear reactions called fusion and fission. In fusion, smaller the nuclei combine together. Okay, so in fusions usually happen so that it is to gain higher binding energy. So it is going trying to reach to that maximum binding energy value by through fusion, where the smaller nuclei combine together. And when you have a bigger, heavier nuclei, they tend to undergo fission, meaning breakdown, and getting into smaller pieces, again trying to reach that maximum binding energy value. Okay, so this is all about stability. That's what we can see. We are going to talk about fusion and fission later. Right, so that mass defect, the mass loss, we can convert it into energy by using the Einstein's equation, E equals mc squared. Right, here is an example. So let's say here, calculate the average binding energy for lithium-7. The mass of lithium-7 atom is this much. U means AMU, atomic mass unit. Okay. So here what you have to do is, first you need to know how many neutrons are there, how many protons are there. Okay. And then you can simply apply this equation to get the mass defect. Okay. So here you are given the information you need, the mass of the neutron and the mass of the hydrogen atom. Once you get the mass defect, so this is the mass defect, you can apply the Einstein's equation. You have to convert this unit. This is a unit conversion. You are converting it into kilograms. Okay. 1 AMU is equal to this much of kilograms. It's just a mass conversion. And then C is the speed of light, which is 3 into 10 to the power 8 in ms to the power minus 1. Okay, m per second. meters per second. Okay. Once you get the joule, sometimes this question might ask you to determine the binding energy values in mega electron volt. In that case, this is the conversion. If you are going to need these values for a calculation, I'll provide you. You don't need to buy hard these values, okay? But you need to know how to determine the mass defect for a given nuclear equation or a radioactive decay, and you should know how to use the Einstein's energy equation to calculate the binding energy value. That part you need to know. The data like this I will provide you. Here is another example. Since we don't have time, we are running out of time. I'm going to quickly go through, because once I upload this presentation, you will have these workouts, the calculation, so that you can try it yourself. Here, this is a radioactive decay process. Radium is converting to xenon after an alpha decay, and they ask us to calculate the decay energy in mega electron volt. So what you have to do, you just simply have to calculate the mass defect occur during this decay process. Okay, so get the difference between the radium mass and the mass sum of the xenon and helium mass. Okay, masses, and then once you calculate the mass defect, you just simply put the Einstein equation there. Any questions? Right. Then another fact that you need to know is that certain nuclei are stable, right? We could see that some are stable and many of them are not stable. See, some are stable, many of them are not stable. If you carefully look into the neutron number and the proton number of these stable nuclides, you will see they are even numbered. Okay, that's an observation. This is not any mathematics or anything else. It's just observation. So nuclei with even number of protons and even number of neutrons are particularly stable. If they have odd numbers, they are usually unstable. And there are some extra magic numbers like 2, 8, 20, 28, 50, 82 likewise. They are, we call magic numbers when the proton or the neutron numbers are magic numbers. They are specifically stable. Right. So based on these ideas, we can determine which one is stable and which one is not. Can you predict which one is not stable here? Out of these three, which one is not stable? What is the answer? Which one is not stable? So no one is answering my question. Which one is stable? Very simple question.
Calcium.
Calcium is not stable. Why? Why it is not stable? Huh? Answer me. So I asked which one is not stable. Someone is giving me a answer in the chat box. Yes, correct. So I asked what is not stable. See, this fluorine is not stable because it has an odd number of atomic number. I think that someone gave me the answer calcium because they were not listening to me, because they were maybe looking at the question. The question is what is specially stable? Then in that case, you can say calcium and oxygen because they have magic numbers. Okay, so this kind of question you can expect. I'm not going to discuss much. Okay, so very easy. Then we will go into nuclear reactions. So a nuclear reaction is a process in which the atomic nucleus changes. It could be a spontaneous radioactivity because that also changes the nucleus, or artificial radioactivity, meaning that we are going to stimulate the radioactivity, okay, by bombarding it with certain particles, okay, or it could be nuclear fusion or where the smaller nuclei come together to produce new nuclides, or nuclear fission where the huge heavier nuclei break into several pieces, okay. So it could be, those could be some examples. Then you have this nuclear transmutation term in your book, that is simply creating one chemical element is generating or converting into another chemical element. So that changing one element to the other, that means the proton number is now changing. That means it should be a change in the nucleus, okay. In a chemical reaction, you don't see these elemental change. So calcium is calcium, whether it is going to undergo any kind of chemical reaction, isn't it? So that's a chemical reaction. No change in nucleus happens, therefore it's the same element. But when it comes to nuclear reactions, it's possible because the nucleus is changing. So it's possible that it is converting from one element to another. If that is the case, we call it transmutation. Right. So when you are writing down this kind of what do you call, like now in these cases, not spontaneous, this artificial radioactivity and like in nuclear transmutation, usually you have to stimulate this. That means you have to bombard a calm nucleus with particles, provoking it to undergo a nuclear reaction. In that case, you are going to use this kind of shorthand notation to indicate it. Now here, see, the boron is bombarded with neutrons, and because of that external stimuli, it is going to break into lithium and into alpha particle, okay. So it can nicely write in the notation. See, this is the starting element. We bombard it with neutrons, and then it is going to undergo nuclear reaction, producing alpha particles and then lithium. Here, oxygen bombarded with proton, then it is going to produce nitrogen and then an alpha decay. Okay, is it clear? The notation is clear. It's not that bad. It's not difficult. Okay, so these kind of notations we use to write those kind of artificial radioactivity or transmutations likewise. See, here are some examples where the how to use these notations, okay? So if a notation is given with some missing information, you can just simply write the equations and balance them using the conservation laws. Mass number and the atomic number has to be balanced. In that case, you can figure out the missing items. Isn't it? Easy. So I'm not going to spend much time. Answers are also given. Please work out on your own and then check the answers with the given answers. Right. I'm going faster because I don't have time to cover everything otherwise. So I told you that we are going to talk about nuclear fission and fusion. So I have a nice picture. Where is it? Oh, here. Nuclear fission and fusion. So nuclear fission, as I said, there is like unstable nuclei, and I'm going to bombard with a particle here as, let's say, neutron, and then it is going to get excited or like create an unstable, very unstable, heavier nuclei, which eventually decay into or break down into several pieces. See, the uranium-236 radioactive, and then it is going to break down, that is called fission, or into barium, krypton, and several more neutrons, and those neutrons are going to attack some more uranium-235, and this is going to go as a chain reaction. So during fission, always, during fission, always energy is released. Okay? During fission, always energy is released. Oh, right? Oh, sorry. Wait. Okay. Then fusion, on the other hand, it's just the fusion. The term itself indicates what it is. Smaller nuclei come together, combine. All right. Smaller nuclei come together, combine, making a new element. All right. In that case, depending on the size, it is possible to release energy or absorb energy. Okay, depending on the size of the new element. Okay, so it could be released or absorbed energy. Not always released energy. In some cases, it may absorb energy when fusion occurs. All right. Okay. So here is an example of a fission reaction. Okay. So in the case of fission reaction, the sum of the masses of the resulting nuclei is now less than the original mass. So that missing mass or mass defect is there. So you can convert it to energy using the Einstein's equation. Very easy. So the information will be given. All right. Here is a question. Consider the neutron bombardment, which releases this much of energy per uranium atom. How much energy would be released if 1 gram of uranium were to undergo fission? Actually, it's not a radio chemistry question. It's actually a unit conversion, isn't it? See, you have 1 gram of uranium. You are going to convert to see how many number of uranium atoms. And 1 atom releases this much of energy, then you multiply it to see how much of energy is released. Anyway, so nuclear fusion. So where the smaller atoms come together and form bigger nuclei. Okay. So nuclear fusion is a process by which multiple nuclei join together to form a heavier one. So I said before that it is going to, depending on what is getting created, it is going to absorb energy or release. Okay. So that depending on the masses. Now, iron and nuclei, I told you they have the maximum binding energy values. Okay. So fusion of 2 nuclei lighter than iron or nickel generally releases energy, while the fusion of heavier nuclei than the nickel or iron, they are going to absorb energy. Okay, that's the rule of thumb. So if they are very smaller compared to nickel or iron, when they fuse together, they are going to release energy. Now, in the case of sun, at sun, what happened? It's fusion. It's fusion of hydrogen and forming helium. Okay. So that happens so many times. Okay. Millions of hydrogen is going to combine together, forming helium. So that's a fusion reaction. So since they are very small, they are going to generate energy or release energy. So that is what we have, the sun, the power, solar energy. Okay. All right. So here is an example of a fusion reaction. Here also, by calculating the mass defect, you can calculate the energy released or absorbed by that particular reaction. In this case, since they are smaller nuclei coming together, they actually release energy. Right. So we will move on to session 4, where we talk about applications of these radio chemistry or nuclear chemistry. Okay. There are several applications. There are medicinal applications, and you can use this radioactivity for dating Dating in the sense that like to date how old a particular element, a particular stone or a rock or a fossil. Likewise, we can use those. And this isotope dilution analysis, since no time is there, I'm not going to explain, but it is clearly explained in page 39. Okay, if you carefully read through, you will understand how the isotope dilution analysis work. So this time I'm not going to spend time on isotope dilution analysis, but I want to explain. This is an example and the answers are given, so no issue there. I'm going to talk about neutron activation analysis. So last year I spent a lot of time explaining isotope dilution analysis. This time I'm going to use time on explaining neutron activation analysis. So in this case, it's a technique. Okay, in this technique, what we do is we are going to use it to quantitatively identify elements. What kind of elements are present in material or a given compound. Okay, so let's see how we are going to use this radioactivity to do this analysis, right? What we do is, let's say we have a sample to be analyzed. What we are going to do is we are going to bombard that sample with neutrons, high energy neutrons, converting some stable isotopes to radioactive isotopes. So we are going to provoke, artificially we are going to create radioactivity. Let's say that we have a neutral sodium sample. We are going to, by bombarding those with neutrons, we are going to convert those 23 sodium, which is the natural neutral sodium, not neutral, I better say non-active, so non-radioactive sodium, into radioactive sodium, 24 sodium, right? So now once they are radioactive, what do? They undergo spontaneous emission. So they undergo radioactive decay, right? Then this radioactive decay is going to emit radiation or particles, and a detector will detect the radiation that emitted, especially gamma rays, because the energy value or the wavelength of the gamma ray that is emitted is characteristic to that particular radioisotope. Not only that, the decay process is also characteristic to that particular radioisotope. So based on that information, the emitted gamma ray especially, and also the decay process, based on that, we can identify what were there before. Based on the radioactive decay of sodium 24 that we created, we can know how much of 23 sodium was there in the original sample. All right. So that's the basic idea of neutron activation analysis. In addition to doing this neutron bombardment to convert the existing material or the element isotope into radioactive isotope, in order to make it more accurate, the analysis, what we do is, to the sample, we purposely add some other standard materials. Those standard materials are also going to get hit by the neutrons and convert into radioactive isotopes, and they're going to decay. But they are standards. We know that they are there, so we can identify them because they are radioactive. We purposely put them and we know what kind of radioactive isotopes are going to be created with those standards, and we know how they are going to decay. We know their gamma ray energy values. So those standards are put there so that we can, rather than having an absolute value for your unknown element or the isotope, we can obtain relative values which is more accurate. Okay, right. So here is an example, like what we do is we have the target nucleus. Okay, so we when needed, we are going to add some standard values or standard isotopes also here, standards also. Then we are going to bombard that with neutrons. Once you do that, they are going to get excited. See, we call it compound nucleus. The term is there. So they are excited now, right? Why? They now converted into radioisotopes, okay? Radioactive isotopes. Then they are going to emit gamma. When they undergo radioactive decay, they emit gamma. So we are going to use a detector to analyze these gamma rays. In addition to that, let's say that after the gamma emission, they are going to produce some more radioactive nuclei. That is also going to undergo now radioactive decay process. This is the gamma ray emitted. We are going to detect. In addition to that, it can undergo further radioactive decay, and there could be another gamma emission that also we can detect. So these informations are going to give us, so those gamma ray energy values and these decay procedure is going to give us an idea quantitatively and qualitatively what were in that original sample. Okay, here is an example using 59 cobalt. So we hit the 59 cobalt, which is neutral, in other words, radio inactive sample. We bombard with neutrons, making it 60M cobalt, which is a metastable radioisotope. It is going to emit gamma and convert to 60 cobalt, which is again radioactive. That is going to undergo radioactive decay. Okay. And again, it is going to emit gamma. So in both cases, we can, by detecting these gamma radiation, we can determine that it was indeed 59 cobalt in there, right? Okay. So that is neutron activation analysis. Theoretically, I explained you what is happening there. Is it clear? Right. So we will go into another application, the dating or the age determination. Now this is simply what we do is we are going to consider how the radioactive element is decaying. We know the half-life value. Depending on how much radioactive element is remaining or left, we can decide or we can determine how much time is being gone. So we are going to do backdate. How long ago this decay started. So therein we can determine how old is the particular object that we are investigating. Okay. For geological dating, because it goes for thousands and thousands of years or millions of years, we use elements having long half-lives like uranium and lead isotopes likewise. Okay. Then for biological dating, to date biological materials like fossils, we use carbon. Why carbon? Because biological materials are made up of carbon, right? Now here is an example. A mineral sample is found to contain 0.211 gram of lead 206 for every gram of uranium-238. Assuming that all the lead in the mineral has resulted from the natural radioactive decay of uranium-238, which takes, several hundred years, estimate how long ago the mineral was formed in the Earth's crust. Now here we assume that there was no lead originally. All the lead that is being created, see this all 0.211 gram of lead created for every gram of uranium-238 is authentically coming from the radioactive decay of uranium-238. So that means before the time elapsed at the T0, this much of lead was also like, whatever the amount of this lead created, it was uranium. Okay, now it is been converted to lead. Okay, that's the logic. So how do you apply this? See, lead to uranium ratio is 0.211 to 1 gram. Why are we saying this? Because it's given. See, 0.211 gram of lead for every gram of uranium. So that's the ratio. But at the beginning of the time, this 0.211 gram was also that it is now lead, but it was before uranium. Now it's been converted. So these are in grams. You can't directly work with grams. You have to convert it into what you call the moles. Here, what they did was they converted the 1 gram of uranium into the number of moles of uranium by dividing it by 238. Here 0.211 divided by 206. Now the number of moles of lead. Now I can safely say at the beginning of the time, this much of moles were also uranium. Now it has been converted to lead because of through the radioactive decay, but initially it was also uranium. So there were this many of uranium at the beginning, a note, but right now I have only this much. This is the ratio. Okay. So we have the ratio. Now you are going to apply to that into our the equation we derived based on the radioactive equilibrium law. Okay. So here, once the N0 to N1 ratio is figured out, we can determine the lambda value because the half-life is given. So you just simply apply and see how long it took for this ratio to occur. All right. Is it okay? Is it clear? Is it why we are using this summation of the two for the N0? Is it clear? Okay, the silence indicates that it's clear, right? Then we will go into carbon-14 dating. So here what happens is, so this is an explanation in words, but this gives it nicely. So what happens is, in the atmosphere, we have the most abundant carbon, which is carbon-12. Then we have a small amount of carbon-13 and then trace amount of carbon-14, which is the radioactive isotope of carbon. Okay. Now, in the atmosphere, we have these all three types of carbon. So the plants and animals like us, as long as we breathe, what we do is we take up carbon in. All these three isotopes we take in, even the plants. Okay. So they store in there, in our flesh, in our blood, in everywhere. It's carbon. So all these three elements, not elements, the isotopes are in our body as long as we are alive and breathing. Okay. So whatever the ratio between radioactive carbon and the other carbons are the same as the atmosphere as long as we live, as long as we breathe, because they are in equilibrium. But what happens if we die? If a tree cut down, now they stop breathing or they stop taking up carbon into their body as carbon dioxide, right? So whatever we have inside our body already as flesh, okay, as bones, or in a tree as the tree stump or leaves or whatever, it's now going to stay there, right? Now they are no longer in the equilibrium with the atmosphere, right? Now inside these the dead animal or the dead tree or the cut down tree, the carbon-12 amount is not going to change because it's not radioactive. So it is going to remain, even in the fossils. Even after several hundred or thousand or million years gone, if they are fossilized, the carbon-12 is remain to be the same. Why? Because it's not going to decay. But what happens to the carbon-14? It's radioactive. So it is spontaneously going to decay. Because of that, once the animal or the plant is dead, the carbon 14 is going to go down because it is decaying constantly. So the carbon 14 to carbon 12 ratio is going to go down compared to the ratio in the atmosphere. So when you use this phenomenon to carbon dating, what you do is you compare the atmospheric ratio and the ratio present in that fossil or the piece of log, right? With that, you can say how long ago this was dead, the comparison. All right, is it clear? So here is an example. A tiny piece of paper taken from the, let's say the story is there, a tiny piece of paper is there. It has activity of 10.8 decays per minute per gram of carbon activity is given. If the initial carbon 14 activity is 13.6, estimate the age of the Dead Sea Scroll. So the activity, it's very simple. Everything is given. A naught is given. A is given. And the only thing that is missing is the lambda, T half of carbon. It is also, even though it's not given in the question, we know it already from previous, don't we know? See, 5,730 years. That's the half-life. Okay. So we know the half-life. Well, we don't know the lambda, but since we know the half-life, we know lambda. We know here it's given N0 to N, but a activity is given. So we can simply say that it is okay to use okay. I hope it's okay because they are like okay to use it. Okay, activity in there, right? So we already established this relationship. Now what you do is you just simply apply these values, A naught and A, and then lambda value, and then you get the answer. The answer is this particular tiny piece of paper was old 1906 years. Okay, here is another question. Do it at home and you should compare the answer with the given answer 3,350 years ago. You do it yourself and see whether you're going to get this. Okay, so with that, we can finish our lecture. Any more questions? Any questions? Any questions from any of you? Sorry. If there are no questions, we can wind up our session. No questions? Okay, so I'm going to upload this presentation so that you have answers. Okay, and some questions to do. So that's it. Then we will have our next day school on symmetry, and then on the 29th September we will have our Cat 2. If nothing, if no questions are there, we can stop the session. All right. Good night.